In this training video, I explained the purpose of calibrating the camera, and I described the various techniques that can be used to achieve the calibration setup. The first question that comes to mind is, why is camera calibration needed? Calibration is required so that the real-world area of tracked objects can be measured. Knowing these areas allows the system to classify objects according to their size so that they can be identified as people and vehicles, etc. For example, once calibrated, the system can be set to only respond to people and ignore smaller objects such as moving trash, dogs, birds, and also larger objects such as vehicles. Also, once calibrated, other physical data can be measured, such as object speeds and heights. In this first video, you can see a person being tracked and causing an alarm event, shown as a red bounding box, whilst the swan is also being tracked but causes no alarms, as shown by the bounding box remaining yellow. This is because in the Properties Inspector, the Include Person filter causes every class of object other than people to be excluded. In the second video, you can see a blue zone set up on the tracking display. Going to the Properties Inspector, you can see the Include Vehicle filter and Speed filter being set so that only vehicle objects traveling between 40 and 200 km per hour will trigger alarm events. Seeing this in action, you can see a slow-moving vehicle being tracked over the zone and causing no alarm event. Likewise, a group of people are also being tracked and filtered out. However, this fast-moving vehicle has met both filter criteria and has consequently triggered an alarm event. In this third video of a car park, there are two people walking about at different distances from the camera. If I turn on the blobs, you can see that, as expected, the blob size of the closer person is the much larger of the two. Now, we know that in real life these two people are fairly similar in size, and it is just the 3D perspective of the scene that makes the distant person look smaller. It is the purpose of the calibration software to correct for this type of perspective effect, so that the real-world area of objects can be measured and objects correctly classified. In this scene, the calibration has been set up beforehand, and so when I turn on the area measurement display, you can see that even though the blobs are very different in size, the measured areas of the two people are roughly the same, at just under 1 square meter each, enabling the system to correctly classify both objects as people. The object classes are fully user-definable on the classification interface, but by default the system is set to have just 4 classes: clutter and person, as shown in the first video, and group of people and vehicle, as shown in the second video. Each class has lower and upper limits of area and speed, which define the class type. So, for example, if we select the person class and look at the area limits, you will see that the lower limit is 0.5 square meters and higher limit is 2 square meters. Therefore, any object that is tracked and its corrected area lies between 0.5 and 2 square meters will be identified as person. Please note that if a system has not been calibrated, the speed and class rules will be missing from the zones and rules interface, and none of the diagnostic properties such as area, height, and class will be available. As with a photograph, a video is a flat 2D representation captured from a 3D scene that the camera was pointing at. What calibration must do is to put back the missing 3D information, and we do this by matching the video scene with a 3D graphical overlay model. Let's start by looking at the 3D overlay by itself. The green grid represents the ground plane, made up of 2 by 2 meter squares, on top of which we have some 3D graphical people that we call mimics. The mimics can be moved about, and they automatically scale depending on their position on the ground plane. We also have other tools, such as a horizon line for checking distances, which can be activated with a right mouse click. Selecting the Draw Horizon option displays a green horizontal line like so. We also have a ruler for measuring the distance between 2 points on the ground plane, which can be activated by right-clicking anywhere on the ground plane to set the anchor point, and then selecting the virtual ruler option and stretching and rotating the other end of the ruler, like so. Notice that as I measure the first square, the values on the end of the ruler show as approximately 2 meters. Increasing this to 2 squares measures at approximately 4 meters. The grid transparency can be turned on to make the grid squares look fainter in order to increase the visibility of the underlying video. As in the real world, adjusting the camera position and settings changes what you see in the scene, and in fact, we only need 3 camera parameters in order to work out all the missing 3D information. The values we need are the camera height, tilt angle, and vertical field of view of lens. So let's see what changing these parameters do. For example, changing the height from 10 meters to 4 meters looks like this. The camera height can also be adjusted by scrolling the mouse wheel like so, which also changes the number in the height dialog box. Likewise, the camera tilt can be changed by typing in the look down angle or by dragging and dropping the grid with the left mouse control. For example, if I change the camera angle from 30 degrees to 0 degrees, the view changes from looking down at the ground to looking at horizontally to the horizon. I can then drag it back again with the mouse. Note that the mimic's feet stay in constant screen position and do not follow a particular grid square. The third and final control is the camera field of view, which can be changed by typing in a number or by adjusting this slider. Another way of thinking about the field of view is as a zoom control. A 40-degree field of view is like a standard lens. A 90-degree field of view is like a wide-angle lens, and a 10-degree field of view is like a telephoto lens. As can be seen, zooming into a narrow field of view makes objects appear closer, just like with a zoom camera. Hitting the restore button will restore the parameter values back to their original state, along with the grid transparency turned on. We also have preset settings for common calibration scenarios. By default, the system is set with a 30-degree look down. The other 2 settings are 60 degrees and 90 degrees look down. The 3D properties of the mimics are shown clearly here, as at 90-degree look down we are looking straight down onto the mimics' heads. Let's take a look at a real-world example for calibrating the camera. To get to the calibration interface, click on the calibration link. On the calibration interface, you can see the live video of a car park with vehicle objects parked everywhere and 2 people wandering about. Let's pause the video on the 2 people, like so. During the normal operation of calibration, the 3D graphics are superimposed onto the video scene. The calibration process, put it simply, is to match the features in the video image to the 3D graphics overlay. This is achieved by adjusting the 3 camera parameters until objects and distances in the 2 worlds match up. When this has been done at a minimum of 2 different points on the screen, then the system is calibrated. Even though this sounds simple, the calibration process can be quite difficult because the 3 parameters interact with each other, and as a result, the user can end up going around in circles. Fortunately, the camera height can nearly always be estimated, and if this is put in correctly at the beginning, it can save a lot of time. Let's type in the known height, like so, and then reduce the tilt angle a little, and place the mimics next to the 2 people in the scene. Decrease the tilt angle until the mimics are approximately the same size as the people. For a further check, use the virtual measuring ruler to measure the width of the car park space, like so, which measures at 2.3 meters, which is about correct for a UK car park space width. Note that the ruler can only be used to to measure distances along the ground plane and not the height of objects. For instance, if I attempt to measure the height of the closer person using the ruler, then we are in fact measuring along the ground the distance between the person's feet and the front wheel of the blue vehicle, which, as you can see, is a much larger measurement and clearly not the height of the person. Once you are happy that the scene is correctly calibrated, click on the Apply button. Going back on the Zones and Rules page, if I turn on all the diagnostic properties, then you will see the corrected information being displayed. To summarize, these are the rules of calibration. Number 1. Measure or estimate the height of the camera above the ground and enter it as the first parameter at the beginning of calibration. Number 2. Adjust the tilt angle and vertical field of view. Number 3. Use the two 3D mimics to match the height of the people or vehicles at both a near and far point in the video, or alternatively use the other 3D graphical tools to achieve the same result, which involve checking the size of known objects using the ruler, checking the distances between objects with the ground plane squares, which are 2 by 2 meters in size, if visible, matching the horizon in the video with the graphics horizon line. Repeat steps 1 to 3 until the 2D and 3D features match fairly well. Plus or minus 10% is normally accurate enough. In this next example, you can see the live video of a riverside with people walking along the path on the left. Let's pause the video when some people are in suitable positions for calibrating the video. One group quite near and one group further away. In this case, the exact camera height is not known, so let's type in an estimated height of 8 meters. Now we know that the horizon lies near the top of the video where the distant trees are situated, and we can use this information to set the tilt angle. Let's reduce the tilt angle a little by dragging the grid down. Enable the graphical horizon, like so, and increase the tilt angle until the graphics horizon roughly matches the horizon in the video. Place the mimics next to the people in the scene. Notice that the mimics appear to be a little smaller than the people in the video, so if I decrease the height a little using the mouse wheel to say approximately 7.1 meters, then they will now match. After hitting apply, the system will be calibrated. In this next example, you can see the live video of a typical indoor office scene. Pause the video on the two people. Notice that the scene has been videoed with a fisheye lens, which distorts the video and makes objects near the edge appear curved and smaller than they should be. Therefore, to achieve the best calibration accuracy with this type of lens, only features in the video that are nearer the center should be used during the calibration process. Let's type in the known height, like so, and then reduce the tilt angle a little, and place the mimics next to the two people in the scene. Decrease the tilt angle until the mimics are approximately the same size as the people. For a further check, use the virtual measuring ruler to measure the length of the room. In this case, the measured length looks a little long, at around 10 meters, when we know that it should be about 6.5 meters. Let's increase the field of view to 64 degrees, which is more appropriate for this type of lens, and change the tilt angle until the mimics match up again. Checking the ruler measurement again gives a better result this time around. In this case, we saw that it is possible to closely match the mimic heights for two different settings of camera angle and field of view. This is quite typical of the interaction between the three camera parameters where their mimic heights can be matched at different calibration settings. This doesn't matter for the classification to work correctly. Either of these calibration settings would have worked okay. The only time you need to check the distances as well is if the speed filter is being used. Hit the apply button and the system will be calibrated. In this final example, we can see many people walking along a road. The camera angle is much steeper in this case, and so at the near edge of the image we are looking almost straight down onto the people's heads, whereas in the far edge they seem to be about 30 or 40 degrees to the camera's axis. So let's keep the estimated height of 10 meters for the moment, and increase the camera angle so that the mimic at the near edge is nearly vertical. Notice that the mimics are not ideally positioned because they are at right angles to the flow of people in the street. So let's open the advanced parameters and pan the ground plane around by 90 degrees. This has also rotated the mimics so that they are now facing the same way as the people in the street. Note the pan and roll advanced parameters only affect the orientation of the 3D ground plane, so that it can be more conveniently aligned with the video scene. The advanced parameters do not affect the camera calibration in any way, and so the height, tilt, and vertical field of view parameters remain unaffected. If we now compare the mimics to the people in the street, the red mimic at the back seems to be too large, so let's adjust the camera height to get it to be about the right size. Adding more mimics can be used to check other points in the image and make a final height adjustment. This can be done with a right click and selecting Add Mimic. One final problem is that the classification is still not working very well, and groups of people are being incorrectly classified as just single people. This is because the camera is looking almost straight down, and because people are long and thin, the view from above is a much smaller area than the side view. What we need to do is reduce the classification sizes for clutter, people and group of people to about 50% of their default settings, and then the classification comes out about right. Note the classification setup is dealt with in more detail in the second calibration video. If we look at the video again, we can see now that the people and groups of people are being more correctly classified.